Hello, and welcome to the Dream9 AML Challenge webinar. My name is Qutub, and I'll be your moderator today. Some quick logistics. You'll be able to type in your questions. Please wait till the end to do so. You can also raise your hand, and please wait till the end after the speakers present to do so again. Briefly, this is the Acute Myeloid Leukemia Outcome Prediction Challenge timeline. The launch party started on June 2nd, and the videos are now up online on YouTube as well as on the wiki site. The AML data was released on the 16th, and the visualization tools came out the next day. Right now, we're going through the optional submission phase, and the final submission is due September 15th. This is followed by the conference, where the winners will be invited to present November 10th through 14th in San Diego. So I'd like to introduce people with me here today. We have Gustavo Stolitsky, who's the DREAM founder, who will first present. And then I'm here with Dr. Stephen Kornblau, who collected the data from MD Anderson Cancer Center. I'll present then, and following me, there'll be Dr. David Noren, who will present on current predictive models, Dr. Byron Long, who will present on the Synapse website, Alex Bisberg, who will give a visualization demo, and Andre Schultz, who will present on the hackathon. Then we'll open up for questions. Now I'd like to introduce Gustavo. So this is Steve Kornblau from MD Anderson. Thank you.
So the next few minutes, let me introduce you to AML, proteomics, our PPA, and better with this? Okay. And the data set for this challenge. So AML is a leukemia or malignancy of white blood cells. About 18,000 cases that will happen this year in the U.S., about 10,500 deaths, and overall about 25% are cured. At MD Anderson, we see about 1.5% to 2% of these cases each year in our single building. If you think about how many hospitals are across the U.S., we see way more than our share of full coverage. Male predominance, whites and Hispanics get it more than African Americans or Asians. As you can see from the chart, your risk goes up a whole lot as your age goes up. Median age is 65 years. This shows how much or how little progress we've made over the decades from the 70s, 80s, 90s, and 2000s overall. And you can see that prognosis has improved more in the under 60 crowd than the over 60 crowd. But clearly there's substantial room for improvement. The traditional clinical prognostic factors for AML were age. If you were over 60, you did worse than if you were under. Cytogenetics, which were loosely grouped into favorable, intermediates, and unfavorables. Whether you had a prior hematologic problem, myelodysplastic syndrome, or maybe therapy related, you'd had prior cancer and had chemo or radiation therapy, and performance status. The problem with these, which I realized a long time ago, and many others as well, is that you can't treat these. You cannot make somebody younger, you can't reverse their history, and you can't improve their performance, make them healthier before you treat them. We tried that once, that didn't work. So you cannot therapeutically target these prognostic features. So you need prognostic features that you can target if you're going to improve outcome. So here's a newer scheme based on cytogenetics and some of the newer mutations that have come along. And again, you can stratify patients better, but the problem is that currently there are not any therapies that attack any of these particular mutations specifically. So you have information, but you still don't have a way to act on it. These are trials, phase 1 and phase 2 trials that we currently have open at MD Anderson for leukemia patients. You can see that they cover a wide variety of different topics and potential methods or attack points within the cells. The problem with a lot of these is that they may work in small groups of patients. And if you think about the statistics, if you have a treatment that is gangbusters, but only 5% of patients, and you do a clinical phase 2 trial, which typically has 14 or 15 patients, the chances that you're going to have a patient who's going to respond to your agent is on less than 10%. And so there's a very high risk that you will discard effective drugs that are highly effective for a small group of patients because you can't figure out which patient should go on that therapy. So we need something that would allow us to do that. We've all probably read the very famous Hanahan and Weinberg paper on the hallmarks of cancer. And all cancers supposedly have to meet these 6 criteria to become malignant. From the TCGA trial, or paper that was recently published, they identified 23 common mutations that are existing along with the limited number of fusion proteins that we have. And they were able to show that some of these correlate with or against others. Some will give you on circus plots stronger bands and weaker bands. But you can see that a lot of them are rather randomly associated. And this leads to a big dilemma. If you've got all these different mutations occurring in various combinations, how do they combine to meet those 6 hallmarks of cancer every time? Okay? And we really don't have a way to account for how they do that. And this is just mutations, but we know that there are other effects, microRNAs, the microenvironment, SNPs, that may affect this as well. So, not too difficult to take the leap of faith and say, well, proteins exist in networks and signaling pathways, and they translate the genetic event, on one hand, into what's going on in the cell, which has to meet those 6 hallmarks of cancer. And so it wasn't too big a idea to think that maybe there would be recurrent patterns of protein expression that, despite having multiple different upstream mutation patterns, these would coalesce into a more finite set of protein expression patterns, and that these would tell you which are the things to attack in a cell. And we hypothesized that we can use this to identify which therapy to match to which patient. So why couldn't we just use mRNA expression rates? Well, 2 reasons. One, protein correlates very poorly with mRNA levels for the vast majority of proteins. But more importantly, we know that post-translational modification is crucial, and you can't measure phosphorylation, cleavage, urination, simulation, etc. on mRNA arrays. Could we just use traditional 2D gel electrophoresis mass spec? The advantage would be it's non-biased, you get a readout on all the proteins that are there. The problem was that the guys at Anderson that we talked to about this, and granted this was back in 2002, 2003, said that sure, they could do 2 patients a year. We had a lot more coming through. And they also needed an exorbitant amount of starting cells, which if we could take all the leukemia out of the patient, they could then study for us. But if we could do that, we wouldn't need it. So we realized that mass spec wouldn't work either, we would need a novel method. And around that time, Lance Leota and Camille Petricoin had come up with this poorly named but useful methodology called reverse-phase protein array, in which you print proteins on a slide, you probe it with an antibody. The disadvantage is that you have to choose the proteins that you're going to look for. It's bias. You have to have an idea of what you want to look for. And not every protein is going to have an antibody. So it was good for this, but it was good only for retrospective analysis. But it was very quantitative, bigger dynamic range than we saw with Western blot, good intra and inter-slide reproducibility. The way we do this, we print protein onto slides in 5 serial dilutions, probe it with a highly validated primary antibody. We validated 280 of these so far, 230 are one of use of this sample set. Probe it with a secondary antibody that has a signal. We precipitate a brown dye, scan the slide, use a program called MicroVGene or others available as well to convert this into numbers and do a lot of statistical manipulation to get rid of background. So on this data set, and we were fortunate to receive funding from the Leukemia and Lymphoma Society to do this, we created an array that had samples from 511 AML patients. 49 of these we had a paired relapse sample. Those are not part of this work. Samples could be either from the marrow or the blood, and we were fortunate enough to have same-day samples, 140 of them, and from these we learned that blood and marrow were equivalent for protein expression. Samples could have been prepared fresh on the day we got them or from cryopreserved cells, and to see if there was a bias in using cryopreserved cells, we made samples from frozen cells from 58 where we had fresh, and for the most part in AML, fresh and frozen are indistinguishable. That's not the case for ALL. Our patients were typical of all AML patients, a little bit more male predominance, age around 65 years. We have a very high percentage of patients that had an antecedent hematologic disorder and prior malignancies. Consequently, we have a lower than typical percentage of patients with favorable cytogenetics and a higher percentage of patients with unfavorable cytogenetics. For this data set, we wanted to make it a little bit more homogenized to answer the questions that we have. And so some of these 511 patients were not treated at MD Anderson, so we eliminated them. And some of these patients died early, under 4 weeks. You could have all the good favorable prognostic features, but if you die of a heart attack on day 3, we can't really score you for outcome. So we cut those patients out. And then we limited it to a group of more standard therapies that use an agent called cytisinorabinuside, which is the backbone of most AML therapy. We cut out some of our more experimental trials. So this left us with a group of 323 patients. And they're pretty typical of leukemia patients. Roughly 2/3 achieve CR, 2/3 of those relapse. And at the end of 4 years, and we have 4-year follow-up on all but 2 or 3 patients, we're left with about a quarter of the population that's still alive. The data fields in the data set include traditional demographics, prior history questions. We have genetics, we have mutations on FLT3 and NPM1 and RAS, many clinical laboratory and flow cytometry measurements, therapy outcomes for whether patients achieved remission, relapsed, if they got a transplant, are they alive or dead, how long they lasted in each of those studies. And then we have the proteomics in which we stained with 231 antibodies. So on this slide, white is a total antibody, yellow is a phosphoantibody, blue is a methylation, and the pinks are cleavage states. And you can see that we're very heavily weighted to signal transduction, autophagy, apoptosis, a lot of cell cycle regulation, a lot of other proteins that regulate other functions within the cell. We've used this to publish several papers on individual proteins while we've been working towards a way to have a global omnibus analysis. And we've even recently, including a paper with Amina's group, looked at functionally related groups of proteins and the ability to build networks. But what we've really wanted to do was to look at proteins as function-related classes together and see what patterns we see. And this is work we've done with Amina's group and Wendy, and I think Amina's probably going to tell us more about that in a second. But we're very excited to be able to look at networks, and we can break patients down by cytogenetics or by particular mutations and see different patterns of protein expression and activation within those, which we think will allow us to eventually target therapy to that. And I'll stop.
Thanks, Steve. I'm actually not going to present on my research. For that, I'd really like to have you reference my publications or ones that are coming up. Instead, I'm going to go over for this webinar, again, reiterate the dates that are upcoming and introduce the data. You can see that the points to remember are the hackathon, July 26th through 27th, the final submission, the 15th of September, and the DREAM conference in November. So right now, I encourage everybody to be finalizing their teams if they haven't already, and submitting for the optional submissions so they can get scored. Once the final submissions are in on September 15th, those top models will be vetted, and the writing phase for the submission to PLOS Computational Biology will start. So I want to highlight some of the benefits of this challenge. One of the clear ones is clinical in terms of improving our ability to predict AML outcome and survival. But a particular benefit of using the proteomics dataset here is that we can tie those outcomes to markers which could have actionable impact, meaning that you could look at targets which are new, find novel biomarkers, and novel drug therapeutic targets. We also have benefits which are technical. An obvious one, of course, is developing new algorithms to interpret the high-dimensional clinical data, but also optimizing existing methods and identifying which are the general algorithms which are best performers on this type of data, and using an objective way of doing so. Finally, also, we're looking at ways to optimize and visualize and sharing raw omics data. And we want your feedback on the new visualization for this platform, this AML platform, Dream Challenge. One of the key points of this I want to highlight is determining whether prior knowledge contributes significantly to the best performance, meaning you are allowed to use outside information to inform the way you design your models, and encouraged to do so. So these are brief definitions. First, primary resistance, meaning you're resistant, the patient is resistant to the given therapy. Complete remission, where there are no signs or symptoms of the disease. And the remission duration, which is the length of remission in weeks. And the overall survival, which is again length in the weeks for each patient following the initial diagnosis. So these are the challenge questions. The first one is to determine the best model to predict which AML patients will have complete remission or will be primary resistant. Answers to this question will help speed the pace of clinical decision-making. It will identify patients who do and do not respond to the current therapies, and results will provide clinicians with a way to better guide therapies. The markers uncovered as most predictive will provide potential new drug targets and insights into the mechanism of AML. Sub-challenge 2 is to predict remission duration for patients who have complete remission. Answers to this question will help us understand the course of AML, and it will identify from clinical and protein data which patients respond to therapy and remain in remission, and those that achieve remission but still die from leukemia. This knowledge will help with clinical decision-making on what course of therapy each patient takes, as well as how patients plan for the future. In sub-challenge 3, challenge participants are asked to predict the overall survival time for each patient. And this is an interesting sub-challenge because despite going to remission, survival time is limited for some AML patients. Conversely, despite relapsing, some AML patients survive longer than those who achieve remission. Unraveling the clinical and molecular features of this puzzling observation will provide insight into AML and will help oncologists better tailor therapies. And by identifying the unique signatures for the worst and best responders, based off of the survival of patients given the current standard ARC therapies, this sub-challenge can provide a set of clinical, genomics, and/or proteomic targets for AML therapy. So this is the AML dataset description. There's 191 patients in the training dataset, 100 in the test data set. All the patients in the training data set and test were seen at MD Anderson and treated with ARC therapies. 2/3 are given for the training, 1/3 is saved for scoring, 100, of which 100, from these 100, a random 75% is used for scoring each week. These patients in the training and test sets have 40 clinical correlates, including mutation status and cytogenetic categories. Outcomes are provided for the training set, and there's 231 protein expression levels provided for both the test and training. So I encourage you to use the new visualization software platform to look at this data set. Alex Bisberg will talk later in this webinar about this specific visualization platform. You can see just immediately here that you have a data selection panel where you can look at all the proteins, the clinical correlates, the groups, and the patients. Now I'd like to turn it over to David Norin, who's going to talk about our current predictive models.
Thank you. We're going to be adding some information to the wiki that includes a description of some general models that can be used to approach the challenge questions, as well as providing an indication of their performance. We're motivated to do this for 2 reasons. First, we've been approached by several people who are very interested in the challenge and the challenge questions, but don't have a strong background in either statistical models or machine learning methods. We hope that this information will be a useful resource towards approaching the challenge questions, as well as be educational in general. Second, we realize that the duration of the challenge is somewhat short compared to the sophistication of the questions that we're asking. We're hoping that by providing participants with performance measures for these general models, like the RSC curve I've shown here, that we can accelerate your progress in making more sophisticated models. So please keep an eye on the wiki for this information and feel free to discuss these models in the forums.
Thanks, Dave. I'd like to follow up on what Dave presented on the current predictive models and also encourage you to go back and look at these challenge questions. We're having additional incentives for those top performers on each sub-challenge who include RPPA data or the proteomics data as part of their contributors to the model. The rationale for this is to have actionable targets. To treat patients, you need to look at protein expression levels, and these would be potential drug targets in the future. So now I'd like to turn it over to Dr. Byron Long, who will present on the current AML challenge logistics and introduce you to the Wiki Synapse site.
Thank you. I'll be talking about navigating the Synapse website, including joining the AML challenge, downloading datasets, submitting predictions, viewing leaderboards, asking questions on the AML challenge forum, and I'll also say a little bit about the scoring metrics that we'll use. First of all, in order to join the AML challenge, you need to go to the Synapse website at synapse.org. In the search box, you can then enter AML challenge, and that should bring you to this page. If you haven't already registered, you can by just clicking on the register link that I've called out with the red circle. Once you've done that, you can scroll down and then click on the Join the AML Challenge button. You'll need to do both because by joining the AML Challenge, you will have access to the data and also you will have the ability to submit predictions. In order to access the data, you can simply click on the Access the Data button, which brings you to the page here with the data, both the scoring data and the training set. In order to download them, for example, the training data set, simply click on the training data button. It will take you to this page. And then to actually start the download, click on the downward pointing arrow button following the file name. When you're ready to submit a prediction, you can just click on the Synapse logo, which will take you to your own homepage on Synapse. And you'll need to, if you haven't already, create a project. You can do that by typing a project name into the text box and then clicking on the Create Project button. When you do that, your project will appear in the My Projects box. At this point, we just have to do two things. One is to upload the file to the Synapse server, and the second is to actually submit it to the challenge. In order to do that, go ahead and click on your project, which will take you to this page, and then upload a file. Click on the Upload or Link to File button. After you do that, you will be able to upload a file and it will appear in your project page. For example, I've uploaded a subchallenge1 predictions.txt file. In order to actually submit that, click on that link, which will take you to a page for the file. And on the far right-hand side, click on the Tools button, which will produce a menu, and then you should click on the Submit to Challenge menu item, which will bring up a dialog box where you select the particular sub-challenge you would like to submit the file to. And in addition, we ask that you provide a team name that will be associated with the submission. Now, submissions will be due each Monday at midnight Central Daylight Time. Shortly thereafter, we will be publishing leaderboards for each of the sub-challenges. You can find the leaderboards by clicking on the link on the left-hand side of the page or by using the View Leaderboard button. And when you do so, you'll see the rankings of everybody, of each team that is submitted during the week. We include their scores and their rankings and their overall rank. If you have any questions, you can simply click on the Ask Questions button, which will take you to the AML Challenge Forum, which looks like this. Questions that have already been asked and answered appear in red. If you'd like to ask a new question, in order to do that, first click on the Community button, which I've called out in red, which will take you to this page where you can type in the text of your question and then continue by clicking on the Continue button. The server will attempt to find similar questions to the one you've asked, and if not, you have text boxes in which you can enter more detailed descriptions of your comments or questions. We request that you also select under the related products and service box, the Dream 9 Acute Myeloid Leukemia Challenge. So that will guarantee that your question is quickly routed to the AML Challenge forum where other people can see it. Now a word about the scoring metrics. Each sub-challenge will be scored by a pair of metrics, beginning with the first sub-challenge, which is to predict a complete response or treatment resistance in terms of a confidence. The first scoring metric is called balance accuracy, which is mainly computed by the summing of two ratios, the first being the true positives, which are the predicted positives of your model, which are correct, divided by the actual positives, summed with the true negatives, which are the correctly predicted negatives by your model, divided by the total number of actual negatives. By positive, I mean your predictions of complete response, and negatives are your predictions of treatment resistance according to the confidence levels in the table. The second metric is called the area under the receiver operating characteristic curve, which plots how true positive rates vary according to false positive rates. The larger the area under the curve, the better the predictor. In order to vary the false positive rates, we vary the threshold at which we consider a prediction to be positive or negative by some value k that ranges between 0 and 1. The second and third sub-challenges, which involve predicting remission and overall survival lengths, are scored by the same pair of metrics. The first one being the concordance index, which is a conditional probability that two predictions are ordered in a particular way, given that the actual values are ordered in the similar manner. So PI and PJ refer to the predicted lengths of either remission or overall survival length for patient I, and AI and AJ refer to the actual lengths of remission or survival lengths for patients I and J. There are some details to this computation that I'm not mentioning here, and I encourage you to see the wiki for more details. The second scoring metric is called the Pearson correlation coefficient, and it's a measure of how well predictions map to actual values. Here, P bar and A bar refer to average predicted lengths and the average actual lengths for remission and overall survival. Again, there are details here that I'm not mentioning. I encourage you to see the wiki for details.
Thanks, Byron. Next speaker is Alex Bisberg, who's going to present on the visualization platform that's new for this year's Dream Challenge.
Hey everyone, my name's Alex, and bring you this visualization platform through Data's Beautiful Solutions with the compute support of Ken Kennedy Institute. The visualization platform displays the full AML training dataset in 4 panels or modules. The data selection panel, a protein heat map, survival curves, and clinical correlate heat map. In the data selection panel, you'll be able to select the proteins, the clinical correlates, patient grouping, and the specific patients you wish to include or exclude for displaying. As you make selections, you can see the data being rendered on the right in 2 circular heat maps. The heat maps are interactive. Think of them as wheels with each spoke representing a different patient. In the top heat map, the 3 proteins I selected are displayed radially for each patient or spoke. The color for each variable represents the level, low, dark blue, to high, bright red. To organize by a specific protein, I click on its title. The bottom heat map works similarly. It displays what I selected as clinical correlates. Age at diagnosis and prior antecedent hematologic disorder are displayed. To organize by age at diagnosis, I click on its name. What if you want to group by a specific category like gender? I click the group I want visualized. The 2 arcs display gender, green for male, yellow for female. After selecting groups, a legend will appear right below the data selection panel. This tells me which group is represented by which color. How do you focus on one group at a time? Clicking on the green arc for male gender displays only the male patient's protein levels and clinical categories. How do you get back to the original groupings? To get back to the original 2 gender groups, you can just click on the center of the circle. What if you'd like to add or change groups? This can be done easily by going back to the selection module. Here I've clicked on prior malignancy and it's added as a group. Then I can unselect gender to display history of prior malignancy alone. Another helpful feature is the ability to focus on one patient's data. By clicking on a single spoke, the heat map highlights this patient's values. Note that the heat map module will sync. At the same time, a red dot highlights the patient's survival. This way, you can track outcome for particular patients as a function of protein or clinical feature. When you click on patients from the protein heat map, clinical heat map, or survival curve, the other two modules update simultaneously. Thanks everyone, and if you want a demo of this for your own data, let us know.
Thanks, Alex. Our next presenter is Andre Schultz, who's going to present on the hackathon.
So we would also like to take this opportunity to invite you to our hackathon, which will take place on July 26th and 27th. We'll be here in Houston, but you can also join us over the internet in the same type of webinar. We will have all participants present on their ideas, so you can receive feedback and you can see what other people are doing and get some ideas for your own project. We will also have people present on different data analysis software and possibly visualization. We'll also have everyone's contact information so you can network, ask people questions, possibly even join teams and form some good collaborations. So please join us July 26th and 27th for the hackathon. Thank you.
Thanks, Andre. I'd like to conclude by thanking everybody who's been involved in the challenge. You can see the list here. Thanks so much. And now, welcome you to the Dream AML Challenge and open the forum for questions. So we have this first question: how to join the hackathon from a remote location. Andre, can you answer that?
Yes. So to join the hackathon from a remote location, we're going to do something similar to what we're doing right now. So we're going to set up a webinar, and in order for people to present, we're going to switch who is sharing the screen. And over the webinar, we'll have people ask questions, and they can raise their hands like you guys see here in the webinar, or even we have released their microphone for them to ask questions, and we'll do all the presentations for the remote presentations over the webinar.
Thanks, Andre. This next question: is the latest uploaded prediction or the best performing prediction scored?
For the final rankings and determination of the winners of the challenge, only the submissions made and for the final deadline will count. However, at each week, for the rankings and scorings of those submissions during the week, we will only score and rank the latest valid submission of each team.
Yes, and each week is new. Thanks, Byron. So the next question is, when is the webinar going to be up? Well, the webinar is going to be up as soon as we finish and wrap it up and get it uploaded. Then the last question, will there be benchmarks posted? I'm going to hand this over to Dave to answer that question.
Thank you. So as I mentioned before, we'll be publishing or posting a number of general models, and these can serve as benchmarks and will be added to the leaderboard. These models, I say, are general because we won't be doing any sophisticated feature selection, nor will we be doing any detailed treatment of the RPPA data itself.
Great, thank you, Dave. That looks like we're done for questions. So thanks, everybody. Thank you, Gustavo.